Hello and welcome back to Calculus 2, section 8.8 on numerical integration. Not every function can be integrated. For instance, integral of sine x squared. Sine squared x, you can use the formula, power reducing, and work on it. But for this one, nothing you can do. And there are a whole bunch of other possibilities that we cannot integrate by any methods we know. Numerical integration is for definite integrals to look for area under the curve, and in this section is going to be a huge improvement on what you learned in Calculus 1. So in Calc 1 you learned area of the left and area of the right. So what does this mean? Area at the left was when you had some kind of a function, you cut down these into those rectangles. You label your first one as x0, and then x1, x2, x3, x4, where x0 is a and x4 is b in this case. And if you are using the left sums, you went into the left corner and you used the left corner to draw these rectangles and then calculate area of these rectangles. And when you calculate the area of the rectangles, that was approximating the actual area. So area L was approximately equal to the true area. You also had area to the right, and that was also in Calculus 1, where you had the same picture, let's say, same function. And you also made these cuts into 4 rectangles. You can put as many rectangles as you want. x0, x1, x2, x3, x4 was the partition on x-axis. But now you went to the right and you drew these rectangles. You see that in the blue case, the fourth rectangle is actually 0 area because it's all the way on the floor. So looking at this method has a lot of error above. Oh, that's error, that's error, that's error, right? It has a lot of error. So the red side, right, in this case, the left one, overestimates the area by a lot because, look, this is almost double. Right, error is as much as the actual space. That's terrible, right? So on the other end, look at the last rectangle. It's 0, right? Calculation gives you 0, so all of this over here is error. So both of these methods, you had to use a lot of rectangles to come up with some nice precision, right? Well, now we're moving to Calc 2 and we are learning 3 methods that will approximate this much better. You see over here, you are approximating the curve with these lines that are all like a constant functions, right? Is there a way to write the constant function better so it approximates function better? And the answer is yes. If we compute the height of the function, not at the end points of the rectangle, but in the middle of the rectangle, in that case, you will get better results. Now let's see why. So midpoint. First rule of engineering, draw big so you can see. Cut in half, cut in half, cut in half. before you went to the left or the right to create a rectangle. Actually, you know what? Let me explain that on this rectangle here. So you went here or here, and it doesn't matter which way you do it, you will get a lot of error. If you do it this way, you get all of this as error. If you go this way, you get all of this as error, because only this would be calculated and the upper part would not be calculated at all, so it introduces error both ways. Now midpoint says, instead of using the endpoints, which are these x0s and x1, right, all of these, instead of using those points in a partition, go to the middle point of each of these and go up from there and draw the rectangle wherever the midpoint hits. So when I draw these rectangles now, they look like this. Oh, this is so much better, right? Because look what's happening for our errors. On one side, you undershoot, but on the other side, you overshoot. They're not the same, but they're roughly there. This is so much improvement over having it either here or here all the time. You see that? Either one of those two blues will introduce a lot more error. Either all of this is error or all of this is error, and that's bad. But if you consider the red only, oh, so good, because your two errors, one error is negative, the other error is positive, and when they combine together, there is still an error, but it's so much smaller than both of those that you learn in Calc 1. It's unbelievable. So we want to keep that error around. I mean, that method around. No, I can't do this. I'll just give up. So now, instead of calculating at these points x0, y0, and so x0, x1, x2, and so on, we will be calculating at, let's do it in red, the average of these. So this is x0 plus x1 over 2, x1 plus x2 over 2, x2 plus x3 over 2, and so on. We already know that x1 minus x0 is delta x. So delta x is something that you calculate b minus a over n. N is the number of rectangles. So this formula from Calculus 1 is not changing. And this delta x is in between every two black lines over here that we have. So there is a delta x here and delta x here and delta x, right? So each width of these four rectangles is delta x. So now, if I want to come up with a formula for, we'll call it mn, because the n is the number of rectangles. If you have m6, then you better have 6 of these calculations. So mn is going to be the width of the rectangle, which is delta x, times the height. And the height is given by f of x0 plus x1 over 2. So you have to calculate the x value, which is the average of the two on the either side. When you calculate the average is the one that you plug into the function and then multiply by delta x. Next rectangle, same story. Delta x, f of x1 plus x2 over 2, plus delta x, f of x2 plus x3 over 2. Plus delta x, last one, f calculated at x3 plus x4 over 2. So what I did is I calculated midpoints for each one of these intervals. So I calculated each red x location in between the pairs of black locations over there. And when we take a look at this, we can see that we can come up with a formula that Mn, well, this was M4 because it was 4 rectangles. But Mn, we can kick out delta x, and then over here we'll just have f of x0 plus x1 over 2 plus f of x1 plus x2 over 2 plus f of x2 plus x3 over 2 plus, and I'll put dot 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 because we go as high as we need to, because n will tell us how many of these terms we get to have. So this is your formula. And now we can apply that formula to this problem here. Your function f of x is given as x square root of x cubed minus x squared plus x plus 2. That's your function. And let's say you want to do this with n equals 4, so we can actually eventually go home, right? Because can we calculate this on 10,000? Well, yeah, it's just going to take a while. Or you write a code and let the computer do it for you. Actually, I had a student last semester who was coding every single thing that I taught in Calculus 2. He was immediately coding in Java. So he stopped by yesterday to show me one of the projects that he did in Java code for numerical integration. His numerical integration is taking 2 billion, n equals 2 billion. I don't know why. There's no reason for 2 billion, but he's able to optimize code so that the computer actually pulls it off in 7 seconds. So, good. Imagine competing against him for a scholarship or something. Anyway, so now I have my f of x, and I have my n equals to 4. And I have my limits given 1 to 5. So I first calculate delta x using b minus a over n, which is 5 minus 1 over 4, which is 1. So my delta x's are all 1. Perfect. My M4, which means use the midpoint to calculate area, because we are going to have a T next for trapezoid rule, and then S. So you can have M4, S4, T4 for all calculate the same area in a different way, so you're going to get different numbers. So that's why we don't use A4 here. What do I have? I have delta x, which is 1, times function computed at 0.5, because that's the, no, I lied, 1.5, right? Because when you take a look at your partition starts at 1, and then 2, and then 3, and then 4, and ends at 5. Your midpoints, 1.5, 2.5, 3.5, 4.5, and you have your 4 rectangles. So I have function computed at 1.5 plus function computed at 2.5 plus function computed at 3.5, and finally function computed at 4.5. And now it's the matter of computing these things in the annoying formula you have up there. So your M4 is equal to 1 times, who cares? you have 1.5 times the square root of 1.5 cubed minus 1.5 squared plus 1.5 plus 2. If you're Rutgers students, you do this by hand, NGIT as well, on the test. The entire calculation by hand. No calculator of any kind on any of the tests. Plus 2.5 times the square root of 2.5 cubed minus 2.5 squared plus 2.5 plus 2. I'm already tired. 3.5 square root of, I could have done this on a square root of x and be done. We'll be talking trapezoid rule by now. 3.5 cubed minus 3.5 squared plus 3.5 plus 2. And then finally 4.5, kill me now, of 4.5 cubed minus 4.5 squared plus 4.5 plus 2 equals a number. There you go. See? I can solve these things quickly. Did we do the integral? No. If you were able to integrate this in the software and calculate, and so, oh, we also need 1 over 9 in front. This is going to give you some number. Oh, I can teach you a cool method to compute this quickly if you have TI-83 or 84. If you have that stuff handy. If you don't have those calculators handy, then maybe you have a good cell phone, not that Apple crap you buy, and you can install TI-83 or 4 on the phone as an app. Vabbit. They're how?
I was looking.
It's a Vabbit. You have Google. All right, so yeah, I said. All right, guys. So this is the way to calculate these insane things quickly if you have the calculator. Now you don't have it on a test, so but you can use that. The first thing you're going to go is to make sure in mode that you have the normal and the function selected. Those are the two things that you need. And then you go second quick, and then you push the y equals for graphing. Make sure it's empty on y1, let's say, or you can use any y you want. So y1, type in the function as you see it on a y1 line. So that's x, open parenthesis, because we have to do the exponent later. And then you have your x cubed, so x caret 3 minus x squared plus x plus 2. Plus 2. Close the parenthesis and then put caret 0.5 because that is going to give you a half exponent, which is the square root. So the first thing you have to do is you have to put the function inside the calculator. So if you are done with if you're done with the function, the next step is to second quit, and then you go home. All right. So now that you have the function on y1, let's say, push the vars button. It's under this arrow down to the left. You see the vars? Push the vars, and then move with the arrow to y vars on the side. And just hit enter on number 1 on the function. And select which y you put the function under. I put mine under y1, so I'm going to select y1. And it should just print y1 on the screen. Now you open parenthesis, and you plug in 1.5. It will compute the entire function. So this is like a notation f of x. So it's y1 of 1. So open parenthesis, 1.5, close parenthesis, you don't have to close it, and it gives you 3.22 well, let's just go with 3.2, 1 decimal precision, who cares? So the first calculation gives you 3.2. Then you go second, enter. To repeat the previous function, you change 1 into 2. So now it's 2.5. Push enter. Should give you 9.3. If you did everything correctly. Second, enter. Change 2 into 3. So it's 3.5. Gives you 21.0. And then second, enter. Will give you 4.5. It's 39.6. And all you need to do now is to add all of these numbers, and you have the value. So this is the fast way to, now there are other ways to compute as well if you are really crafty with these things. What you can do is you can use a table feature as well. What you can do, since you have your function y plugged in, you can go and say second table set is above window. So go second table set, and you see that it says table start. That's the first value that the table is going to have. Set that to 1.5 because that's your first value. And then you have a delta table underneath. Delta table is the increment. Your increment delta x is 1. So put 1 there and hit enter. When you now go second table, it will give you in the table x values, 1.5, 2.5, 3.5, 4.5, gives you all those values, and the y coordinates are all this. So that's the way to use the calculator, 2 ways to use the calculator to compute all of this. All right. I'm not sure if Apple got to this point in development that they can put that on. But I've been using this for 5 years now, so it's good. Okay, so this is the way to compute, and now you add all of these numbers. These two give you 60, 72, 73.1. I hope. So the area is approximately 73.1. That's what midpoint says. The goal is to calculate the midpoint for each one, and then when you have the midpoint for each one, you just go and compute the function value to get your heights times the delta x, which is your width, and that's it. So you have your formula for midpoint. Next one is trapezoid rule. A trapezoid rule is going to be the linear approximation, because now if you have your, we're going to do the same graph in terms of, the same picture like this, and now when you divide it half, 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 you will be connecting the endpoints with a straight line. Well, that looks good all the way until the last one, right? Now, if you are to, let's say, take number 3 over here and pop it on a side, it would look like this. Right? Now you are used to, I don't know if you know it, the area of the trapezoid is the average of the two sides that are parallel times the height of the trapezoid. So call this A, call this B, call this H. Area of the single trapezoid is A plus B divided by 2 times the height. So that's the area of the trapezoid. Now, if you are to stand this up and plug it back into your picture, you quickly realize that your age over here is delta x, because that's on the floor. Can we all rotate this in our heads and put it like a puzzle piece back in place? Are we okay with that? So do we all agree that age is delta x on the bottom? Excellent. And if this is x0, x1, x2, x3, x4, so what's B?
B is the height.
Good. B is the height. So what should I have? Why? Look at the picture. I am connecting the sides of the one that I flipped on the side over there.
X2. Right? It's f of x.
F of x2. Good. It's the height. X2 is just a location, guys, on the x-axis. That's all x2 is. Location. Like x2 is 6. That's all it is. The height is f of x6. Over here, f of x6. So this is going to be f of x2. And what's A?
X3.
F of x3. Good. So now you see that this area of one of these puppies, so area for the third rectangle over here, is going to be what? It's going to be A, which is f of x3, plus B, which is f of x2, divided by 2 times delta x. Right? Now, if you consider the one before that, it will have f of x1, and it will also have another f of x2. So you see how f of x2 is used for number 2 and number 3 calculation. It's used twice. And then f of 3 is used for f of 3 and f of 4, right? I mean rectangle 4. So each one of these middle ones is used for 2 calculations, one on the left and one on the right. Only the endpoints are used once. We have delta x over 2. That gives us a very simple formula for trapezoid regardless of how many rectangles you have. Trapezoid with the n is delta x over 2. And now in parentheses, you have your f of x0, and it's a single f of x0 because it's the only one calculation, right, for the first rectangle. All others will be 2 times, and you go all of these inside will always have 2 times. When you go to the second to the last one, it's still 2 times, and I put n minus 1 to signify that that's 1 before the end. So if you are doing 9 rectangles, then n is 9, well, n minus 1 is 8, so this is the one before, right? And finally, the last one is single, xn. Use these brackets like this. This is a formula for trapezoid rule. The pattern for these values inside is 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, depending on how many rectangles you have all together. Well, we apply this formula to your precious problem, okay? So your precious problem from before, T4 is equal to 1/2 this one. Now, you know what, it's better if we just do the partition and everything. So your f of x is equal to x square root of x cubed minus x squared plus x plus 2. We are using 4 rectangles. We are using trapezoid rule. We are on 1 to 5. You make your partition. First number is 1, then 2, then 3, then 4, and then 5. So partition will have 5 numbers. Now, partition has 5 numbers. And there are 4, right? There is n equals 1, n equals 2, and 3, so 4 rectangles. So now, you follow the formula. You know that delta x, right? Delta x is the same as before, b minus a over n, which is still 1. And now you get to put the formula together. So T4 is going to be 1 over 2. And now I have to calculate function at 1 plus 2 times function at 2 plus 2 times function at 3 plus 2 times function at 4, plus a single function at 5. The first and the last do not get times 2, because they participate in calculation only once. And now you go in your, you can use the table, it's still the same function. So I'm going to open up table set, and I'm going to start my table at 1 with the increment of 1. And hit second graph, which gives me the table. So T4 is 1/2, open parenthesis, 1.7 plus 5.7 plus 14.4 plus 29.4. Oh, I need to double these. Hold on. Plus 2 times, 2 times, 2 times. I forgot to double them. And then finally, the last one is 51.7. And now you compute this, and you're done. So 0.5 times, open parenthesis, 1.7 plus 11.4 when you multiply, plus 28.8 plus 58.8 plus 51.7. It gives 76.2. So area is approximated by 76.2 using trapezoid rule. What did we have earlier? 73.1. 76.2. They're 3.1 units apart. So for trapezoid rule, you have to partition again, get your x0, y0, x0, x1, x2, x3, and x4, and plug them in the formula, making sure that the first and the last have their coefficient of 1, and all of the ones in the middle, they should have the coefficient of 2, multiplying them. Now, if you think this is annoying to memorize, 1, 2, 2, 2, 2, 1, let's see what Simpson's rule has to say about approximation. First, right next to the title, Simpson's rule, in blood, I get to write n must be even. So, if I ask you to compute Simpson's rule with 5 rectangles, you know I'm trolling. You just say, not possible. And you're done with the problem, right? Simpson's rule only works if you have even number of rectangles. Obviously, there is a proof for Simpson's rule, and that's what you also see that n has to be even. That Simpson's rule is fitting parabolas. So if you are approximating, you wouldn't not approximate the quadratic formula with this stuff because you can integrate, right, to get the area. X squared, not a problem. Right? Integrate x squared, you get x cubed over 3, plug the limits, you're done. There's no reason for a sledgehammer, right? But if you are to use this method, Simpson's rule, on a quadratic function, you will get exact answer. Because Simpson's rule approximates the functions by putting in small quadratic arches inside. So you saw that left rule, right rule, and midpoints were all flat. Those are constant approximations. Then you have your trapezoid rule, which was connecting 2 points, and the angle, it's a linear approximation. Now you have a Simpson's rule, which is going to fit through every 3 consecutive points a little x squared arch. And that one is Simpson's rule. One rule that you are not learning here, but if you take numerical analysis in the Fourier school or go graduate school, cubic splines. Cubic splines are going to fit cubic pieces. It doesn't end with what we have in the class. It just goes on and on and on. So Simpson's rule, much trickier to derive. We do teach it in numerical analysis if you're interested. Simpson's rule, n must be even. That's rule number 1. Now, your Sn formula is delta x divided by 3. So midpoint, delta x was not divided by anything, or divided by 1. Trapezoid divided by 2, Simpson divided by 3. So they lined up nicely, 1, 2, 3. Right. Now, what's the rule? The rule is you have a single, so one time, or just put f of x0. So the first one is single, just like in your trapezoid. Now the second one is times 4. So plus 4 f of x1. And the third one is times 2 f of x2. Plus, it goes back to 4 f x3 plus 2 f x2 plus dot dot dot. So what's the pattern? 1 4 2 4 2 4 2 4 2 4 2 4 2 4 2 4 2 4. It just keeps swapping those two. So trapezoid rule 1 2 2 2 2 2 2 2 2, right? And Simpson 1 4 2 4 2 4 2 4 2 all the way. Now it has to end with 2 4 1. So we have 2 f of xn minus 2 plus 4 f of xn minus 1 plus single xn is the last. So I know this formula is convoluted, but now we're going to do our problem with this. So your midpoint has coefficients of 1. The trapezoid rule has all the 2's inside, and Simpson alternates the middle for as many rectangles. Now, this is why you must have even number of rectangles. The pattern cannot fit. If you have 5 rectangles, you can't fit 1 4 2 4 pattern because it will end on a wrong number. You are required to alternate 4 and 2 for as long as you have to go, and you have to end symmetrically. So if it was 1 4 2, you have to end with 2 4 1. So if you take a look, here is one rectangle, here is one rectangle, here is one rectangle, here is one rectangle. So 4 rectangles. If I extend, here is one, here is one, here's one, another one, another one, another one, another one, another 1 2 3 4 5 6 7 8. It has to work. So it must be, number of rectangles must be even. All right, what is our function? Our favorite function, sponsored by you guys, is f of x is x square root of x cubed minus x squared. I'm gonna dream this damn thing, plus 2. We have okay, so we have the Simpson's rule with the 4 rectangles, so S4, and we have the 1 to 5. Everything stays the same. You first go make your partitions. So 1, 2, 3, 4, and 5. And you know these are partitions with delta x equals 1 because our delta x is still the same, b minus a over n, which is 1. So now, all I need to do is to plug this in. So S4 is going to be 1 over 3 because it's delta x over 3. Delta x is 1, so 1/3 in there. Open parenthesis, f of x 0, well, that's 1. So f of 1 plus 4 times f of 2 plus 2 times f of 3 plus 4 times f of 4 and plus single f5. So the beginning and the end are single values. Now we already have all of these values except the two numbers with 4s, they have to be multiplied by 4 this time around. So what I'm going to do is I'm going to go up and steal this calculation off of the trapezoid rule. It won't let me steal it. Okay, fine. S4 is... Oh, what's going on now? 1/3. It was 1.7 plus 4 times... Oh, actually, I have it here on my chart. 5.7, so 4 times 5.7 plus 2 times 14.4. Why is this being annoying now? What's going on? Two times 14.4 plus 4 times, what's the next number? 29.4, and the last number 51.7. Now we can punch all of this in the calculator. One divided by 3 times, open parenthesis, 1.7 plus 4 times 5.7 plus 28.8 plus 4 times 29.4 plus 51.7 to get S4 is equal to 74.2. Come on. So area in this case is approximated by 74.2. So we had 74.2, 76.2, and 73.1. They're all close, right? 72 and 74 and 76, they're all very close when you talk about 70. And that's the lesson. That's all. Those 3 formulas, the 3 patterns. Remember that the dx is divided by 1, then divided by 2, then divided by 3. That's what we have. No integration, no derivatives, none of that stuff. This is a purely numerical calculation, and I am encouraging those who are computer science to code this using loops. If you're not computer science, code this using loops. Because at least the basic of programming, all of the tools obviously are free, and you can use YouTube to learn quickly enough coding. In 30 minutes you can learn enough coding to code this whole method. Now you're not going to know how to optimize it to use it on a billion rectangles, but let the software calculate 100 rectangles, right? You can just, because you can specify that you wanted to do 1,000 loops. That's like 1,000 rectangles. And you can calculate, it will generate the formula and everything. So everyone in this class should know how to code that, because it's a joke for those who know, and it's very easy to learn. Those skills are good because machines and everything is programmed today, and you program computers, you program machines, you program everything. So, you should know. Bye.